This is an introductory video on composite prepreg layup and vacuum bagging, which is a very popular method of fabricating aerospace composite parts. Let's start by looking at a schematic diagram of a vacuum bag. At the very bottom is the tool. If you were making an aircraft part, this tool would have a negative shape of your part. In this case, the tool is flat because it is for making a flat clipboard panel. Above the tool is a release film, which prevents the part from sticking to the tool. Now, most aircraft parts have some curvature, so release agent rather than release film may be preferred, because it may be difficult to drape or conform the release film over curvatures. Release agent usually comes in liquid or spray bottle form. When properly applied, it leaves a thin layer of release on the tool, kind of like the Teflon coating on our non-stick pan, which will prevent the composite part from sticking to the tool. Above the release film is the composite prepreg layup. This is what will become your part when it is cured in an autoclave or oven. It typically consists of many plies of varying orientations. Engineers will specify the stacking sequence of the laminate based on engineering requirements of the part, such as strength and stiffness requirements. Above the prepreg is another layer of release film, which will prevent the part from sticking to the bagging materials above. The call sheet is usually optional. It is designed to create a smoother surface on the back side of the part. The call sheet doesn't actually give you a mold control surface though. Then, above the call sheet is the breather. Breather is a porous material usually made out of polyester or fiberglass. Its function is to create an airflow path when vacuum is pulled inside the bag. Breather can also function as a bleeder because it can absorb excess resin that flows out of the prepreg during cure. Above the breather is the nylon vacuum bag, which will be the film that keeps vacuum. The edges of the vacuum bag is attached to the sealant tape, which helps create the vacuum seal. This gentleman has just laid down the first ply of prepreg and is rolling it down onto the blue color release film. The white color paper that he just removed is the backing paper, which is designed to prevent the prepreg from sticking onto itself when it was in the form of a roll. He is now laying down the second ply, making sure he has the ply oriented correctly before he starts rolling the second ply down onto the first ply. By the shape of the tool he's laying up on, you have probably guessed that he's simply making a flat panel. If he were making an actual aircraft part, the tool would resemble the shape of an aircraft part, in which case it would be more challenging to try to drape the prepreg onto the contours. After rolling the second ply down, he will remove the backing paper. He will have to repeat the layup process as many times as necessary according to the engineering stacking sequence requirement. Sometimes engineers may call out a debulking step after a certain number of plies is laid down. Debulking will remove entrapped air and help consolidate the plies. Release films are used to prevent the prepreg from sticking onto other materials. Breather is placed above the release film to ensure that there is proper airflow path to the vacuum port. This is a simple debulking table which has a flat bottom and a flexible silicone sheet on the top. This is a room temperature debulk process. Debulking can also be performed at elevated temperature to release volatiles from the prepreg. This lady is in the process of laying up a sandwich panel which has a honeycomb core sandwiched between two carbon fiber epoxy face sheets. She has finished laying up the first face sheet. The green color film is a film adhesive designed for bonding the face sheet to the honeycomb. She has laid down the honeycomb. Next is a layer of film adhesive and then several layers of prepreg to make up the other face sheet. This part will be cured in an autoclave. Edge dams are placed around the edges to prevent the autoclave pressure from crushing the core. A thermocouple wire is placed in the part to measure the part temperature throughout the autoclave cure cycle. If this were a larger or more complicated part, several thermocouple wires will be required to sample the thermal profile to ensure that the entire part is cured according to engineering requirements. Next is a layer of release film. Release film is also known as separator film. As we have covered earlier, this release film will prevent the part from sticking to the bagging materials above it. A call sheet, which in most cases is optional, is used here to achieve a smooth backside face sheet. Without the call sheet, the backside face sheet will likely have dimples due to the autoclave pressure and the flexible bagging materials. A release film is placed above the call sheet, followed by a polyester breather. It is important at this stage to make sure that there is no bridging in the bagging materials that will create uneven pressure distribution on the part. This involves making sure that there is plenty of bagging materials to drape over every contour of the part. When heat is applied on the part in an autoclave or oven, the resin in the pre-preg will flow before it starts to cure. Uneven pressure distribution will cause the resin to flow from high pressure areas to low pressure areas, creating resin-starved and resin-rich areas on the part, which is detrimental to the quality and structural integrity of the part. Where necessary, cut and place small pieces of bagging materials to make sure that there is no bridging. The next and final bagging material is the vacuum bag itself. Note that sealant tape has been placed on the edges of the tool. Make sure that there is plenty of vacuum bag to conform over all the contours. When sealing the vacuum bag onto the sealant tape, start by peeling off the backing paper of the sealant tape and then tacking the vacuum bag onto the sealant tape. Pleats can be made in the sealant tape and vacuum bag to make sure that there is ample amount of bag to conform over contours and no bridging exists in the vacuum bag. Now is the time to install the vacuum ports. We need a minimum of 2 vacuum ports, one for vacuum source and another for vacuum transducer. The 2 vacuum ports should be placed as far apart as possible so that the transducer will be measuring an area farthest away from the vacuum source. Make sure that the breather extends out to both vacuum ports. While the vacuum is being pulled, make sure that there is no bridging in the vacuum bag materials. Bridging, as we have discussed, will create uneven pressure distribution on the part, resulting in resin-starved or dry spots and resin-rich areas. Before a vacuum bag may be loaded into an autoclave, it must be checked for vacuum integrity. Typical aerospace requirement is a leak rate of no more than 3 to 5 inches of mercury over a period of 5 minutes. There are 2 commonly used methods of checking vacuum integrity. The first method, which I'm showing here, is the less proper method because it is not how the autoclave checks vacuum integrity. The hose on the right has been connected to the vacuum bag. After vacuum is pulled in the bag, the shutoff valve is closed and the vacuum is monitored using the vacuum gauge. In this case, the vacuum is leaking in the bag because the needle in the gauge is dropping very fast, faster than 3 to 5 inches of mercury in 5 minutes. This picture shows a more proper method of checking vacuum integrity. Vacuum is pulled from a port on the far end of the bag. The vacuum gauge is connected to the vacuum port on the near end. This is a more proper method because this is exactly how the autoclave will be monitoring vacuum level in the bag during the cure cycle.